Again, like I said, we're going to do this using matrices to transform geometric figures. Nothing very difficult whatsoever. We want to say use geometric figures, and when we do that, first off, we need to change the geometric figure into a matrix. So take this geometric figure, or take these 3 points. A is -2, -1, B is 0, 3, C is 1, -2. What kind of shape would that probably make if you connected all 3 points? Triangle. Okay. Take that triangle and we're going to change that triangle, those points, into a matrix. And it's very easy. All you do is you're going to make an X row and a Y row. And for the benefit of doubt, and since an X row and a Y row, so to convert, you're going to say change it into a matrix. It should be X row, Y row. Okay, what are all the X coordinates? All the X points? -2, 0, and 1. So you would write that on the top row. -2, 0, and 1. And the Y coordinates, what are all the Y's?
-1.
And there you go. You've now changed the points on the triangle into a matrix. That's it. Notice that that first column, -2, -1, is point A. 0, 3 is point B, or that would be the column, but that's point B. And the column that's 1, -2 is point C.
So
X and Y's are the rows, the points are the columns. Yes?
So what is having it like that? What does that do for you?
That allows me to to make the changes. Like what do we do when we want to transform? What are the geometric transformations we can do? Translation, dilation, reflection, rotation. Okay, this allows me in an algebraic way, matrix way, to do those translations or to do those transformations. And that's what we're going to do today. And again, like I said, what photo editing software does, a lot of that is from a matrix standpoint. You don't see it because all you see is the image. But in the background, in the program itself, that's what the computer is looking at. It's looking at the matrix. Okay, so again, our transformations are translation, dilation, reflection, and rotation. Those are the 4 transformations that we deal with. And we're going to look at those today. A translation is just matrix addition, which we covered in 4-1. Okay. A dilation is just scalar multiplication. Again, something we covered back on Monday in 4-1. A reflection and a rotation, both of those are matrix multiplication. So like what we were supposed to be doing yesterday. First, with a translation, like I said, basically what you're doing, you're taking the geometric matrix, the one that you, let's say, made from looking at the coordinates, and adding to it a translation matrix. Now, when we want to add matrices, what do you have to have?
The same amount.
Right, you have to have the same. Dimensions have to be the same to be able to add. So if, like I'm saying, let's say on the first example, that one that we created from ABC, that was a 2x3, what do I have to add to it? I have to add another 2x3. Okay. So let's do that as an example. Take that same points that you had on the last example, A, B, C, which were -2, -1, 0, 3, 1, -2, and I want to translate that triangle 2 units to the right and 3 units down.
Would it be
You got the right idea. Keep going.
+2 minus?
You got the right idea. Now the question is, how do you show that in the matrix? Like, for example, if I change...
The x's and subtract the y's?
Okay, you're right. The 2's, okay, you're getting really close. But you got to show it as another matrix. And if this is a 2x3, this has to be a 2x3. So what should that top row all be?
It shall be +2.
Okay, +2. And since I've already got the plus here, I can just put 2, 2, 2. Okay, and the bottom row is going to be
-3.
-3 all the way across. Okay, so that is now, notice that, the 2 units to the right, that's changing the x, so I wrote down, like, say, to the right, plus 2 or positive 2, and wrote it 3 times because I need to add 2 to each of these x's. So if there's 3 x's on top, I should have 3 adding 2's to it. On the bottom, the negative 3, 3 units down, changes the y. So since there's 3 y's, I gotta have negative 3 times. Negative 2 plus 2 is 0. 0 plus 2 is 2. 1 plus 2 is 3. Negative 1 plus negative 3 is negative 4. 3 plus negative 3. And negative 2 plus negative 3. Okay, and notice, point A, B, C in the first one, if you look at the columns on the last, the answer, it's technically supposed to be A prime, B prime, C prime. Remember, the original ones, we always had like just those letters, A, B, C, but the new ones, you always put that little, like, stick, whatever you want to call it, and they said it's prime, I think. And I believe the original is called the pre-image, and the new one, or the answer, would be the image. I think that's what they called it in geometry. I don't remember.
Well, this is just like getting triangles. Let's say like triangles in the first coordinate, and then all we're doing is translating it. So this is more of an organized way to do it.
It's not only is it a more organized way to do it, but like I said, if you ever get into photo editing software and you ever like start looking beyond like what you just simply see there on the screen and start doing like Photoshop, like. Technically, that's what Photoshop is doing behind the scenes. It's working a matrix, and every number, it has a different color code associated to it, or every color has a different number associated to it. So as you're even changing colors, the matrix is changing based on that. So the native resolution of this iPad screen is supposedly like 1028 by 768, something like that. That in theory means you have a matrix for the screen of like at least 1028 lines and 768 columns.
Oh, like the red, blue, and green.
Yeah.
Oh,
Those are color codes that are associated on a very basic level, probably at a level you may never see, but you never know. You may go into that, may want to go into that field, and now you're kind of being exposed to an idea of where matrices, another idea where matrices can be used.
So the more rows and columns in the iPad, the clearer it is.
Supposedly. All right, now let's look at dilation. A dilation is scalar multiplication. Again, not very hard. I thought transformation is translation is so easy. I only need one example. Dilation, same thing. One example, super easy. All you got to do is, let's say I give you another triangle. Let's say we reduce triangle DEF with the coordinates, I don't even remember. Let's see. The coordinates for point D is -4, 0. Point E, 4, -2. Point F, 2, 4. And I want to reduce it by a factor of 1/2.
So you subtract them all by.
No. Now remember, what are we doing?
Multiplication.
We're doing scalar multiplication. So you would take DEF, make it into a matrix, and you're going to multiply that matrix by 1/2 would be better. Okay, that's all you got to do. Take the D, E, and F, change them to a matrix. -4, 4, 2, 0, -2, 4. And you're going to multiply that by 1/2. -2, 2, 1, 0, -1, 2 will give me D prime, E prime, F prime. So all I did was multiply. Every single number was multiplied by 1/2. Okay? So think of it like distributive properties. Multiply by 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Every single number.
Everything should be.
Let's look at reflection. And there is an important thing to note here. Again, reflection is matrix multiplication. But you're going to multiply by a reflection matrix. So that's something you definitely need to make sure you have in the notes. Because if you use that on the quiz, it's right there. If you have it on your note card, it'll be right there.
So we're going to do the same thing for rotation also?
Yes, it'll have a rotation matrix also. Similar, very similar, but the numbers will be slightly tweaked. So that's what you have to, that's why you got to make sure that you have those notes saying, okay, this is reflection, this is rotation. Okay, so to do a reflection, what we have to do is multiply by a reflection matrix. And it actually is the reflection matrix first. So, like, here's an example. -1, 0, 0, 1 times the geometric matrix. That -1, 0, 0, 1 will reflect over the, should be the y-axis. There we go.
So it's the -1, 0 with that?
Yeah.
Does that have anything to do with that identity matrix? Or?
It kind of does. Because what you're going on here is, like, by doing this, all you're really doing is going to change the sign of the x. Like on this. So it's similar to like multiplying by 1. It's very close, but you're just changing one part. This allows you to just do that. Like when you reflect over the y-axis, you're changing the sign of the x. Okay, multiplying it by that will allow you to change the sign of the x, but not the y. So that, yeah, you're right. There is it's very similar to the identity matrix.
It reflects what?
This one will reflect the coordinates or whatever matrix you have, whatever figure you have, over the y-axis.
Does it reflects y part?
Over y-axis.
Does the identity
Yeah, there should have been more of a space. Just kind of didn't happen.
Does the identity matrix does that always have to be the positive?
Take the triangle JKL, where J is 3, 4, K is 4, 2, L is 1, -2, and reflected over the, should be y-axis. Okay. So the first thing you should write is the reflection matrix, which should be, what's that matrix? No, it's a 2 by 2, but what's that matrix? I just gave it to you in the notes. What's the reflection matrix? -1, comma, 0, or -1, 0, I don't know why I thought comma, and then 0, 1. Take that and you're going to multiply it. Okay, and what should you have on the top row?
So you're always going to have that?
3, 4, 1.
3, 4, 1. Okay, and then on the bottom row?
-2.
There you go. And just multiply it. If you make that multiplication, you will have the rotated, or I'm sorry, the reflected figure. You will have the coordinates of the reflected figure.
But you can't multiply because if they're not the same.
Better? You're doing the whole screen.
But they're not glasses?
Yes? No. Remember. In theory, all that difficult to get that answer.
You're not going to do the. You're not going to do the 0, right? Like you're not going to multiply.
That one I just showed you is just a reflection over the y-axis. You can actually do a reflection over the y-axis and a reflection over the x-axis. And in theory, you could even do reflection over y equals x, but I haven't looked into that one yet. But a reflection over the y-axis, that's the one you use. That matrix that is -1, 0, 0, 1. Reflection over the x-axis, slight tweak,
Now you're just flipping it.
and you just got the negative on the other one. The first one reflects it over the y-axis. Remember, that reflection goes across. The second one reflects over the x-axis. That's the one that goes, say, up and down, flips it up and down. But both of those, you have seen, that would be something very good for the notes, very good for the note card.
Wink, wink.
And rotation, a rotation is very similar. You multiply it by a rotation matrix, it will look very similar to a reflection matrix, so be careful with that. The rotation matrix, there's actually two types of rotations you have to worry about. 90 degrees counterclockwise, and to do a 90 degree counterclockwise, you're going to use the matrix that will pop up right under it. So 0, -1, 1, 0. Clockwise, 90 degrees clockwise, gives you that other, you have to use that other matrix. So these are the matrices you use for rotations. Notice they're very similar, but just slightly different. And that's probably the reason why, like on, say, some very simple, like when I go to, like, I download my photos into my computer, and I, like, if I took one where it was like standing up and it's like showing sideways on the computer, I just press a button. It does like a 90-degree rotation, only 90 degrees at a time. Well, that's like that. It's going through a matrix multiplication to do that. Again, the computers do not see the image. They see programming. So they're dealing with the matrices to do whatever you're asking it to do. Next, let's look at an example. Take this example. A polygon. I decided to do something besides a triangle because I was getting tired of triangles. Polygon MNOP. M is 0, 0, N is 4, 2, O is 2, negative 5, P is negative 1, negative 3. And rotate 90 degrees counterclockwise. So, again, the rotation matrix first. So it should be 0, negative 1. Okay, so 0, negative 1, 1, 0 times, no, 0, 4, like if I'm going across, 0, 4, 2, negative 1, then 0, 2, negative 5, negative 3. Okay, if you multiply those two, and notice, because it's always x and y, x row, y rows, that always makes this a 2 here in the front. And having a 2 by 2 matrix means they'll always be able to multiply. So just go from there. If it was 3-dimensional, then this would have to be extended to a 3 by 3, because there would be an x, y, and 0. But we won't go there. Okay, if you multiply that, huh? Don't want to know. Said we probably don't want to know. In case you're wondering what that's about. Yeah, this is like, I got this and one more example.
What is this?
Rotation, counterclockwise. Okay, if you do that, you get, say, negative 2, 5, 3. This is rotation. The reflection just changes the signs. No, but I'm saying the x and y's flip-flop. Notice here the x's and y's changed. 4, 2 became negative 2, 4. They switched. Okay, now, I can also erase and redo this problem, say 90 degrees clockwise. And that would be 0, 1, negative 1, 0, times all that. Okay, if you do the multiplication there, notice the x and y still flip, but this time the old x's change signs. And that's, like I said, that's pretty much like, say, translation, dilation, reflection, and rotation.
I have a question. Kind of random. What do they use the Roman numerals for? Like, what were they used?
B in the workbook, page 27, all the problems. Yep.